Good morning, everyone. My name is Michelle Sainer, and today we are talking about different periodic trends. We're going to look at how we can determine atomic radii, compare them from one element to another based on their position on the periodic table. We'll learn how to count the number of valence electrons that an element has, and finally, we'll understand a little bit about how different groups on the periodic table have different reactivities. So let's start with our learning target. You'll need to take notes on this video today. It's an expectation that you write down everything that's on the slides, and then you can add in any sort of extra things that you hear me say that you think are relevant. Starting with our learning target, by the end of today, you should be able to use the periodic table to predict the trends of the atomic radius, to calculate the number of valence electrons, and also to determine relative reactivity. Let's start with a discussion of what the atomic radius is, and here's a clip from our book. Atomic radius is defined formally as the 1/2 the distance between the nuclei of two identical atoms bonded together. So let's think about what that means. Here's the nucleus of the first atom, here's the nucleus of the second atom. Radius, as opposed to diameter, would be then this small section that occupies half the distance between these two nuclei. So it's kind of like the center of one atom to its edge, and then the center of the other atom to its edge. And again, we are talking about very, very small things in the realm of picometers. So this is an example of the chlorine Cl2, two chlorine atoms bonded together, where you have the atomic radius of 99 picometers. So take a moment and see if you can jot down, what does this mean to you in your own words? It's helpful to always have a definition that makes sense to us, as opposed to always relying on a book definition. Chemistry is not a subject that you want to memorize. So you need to make sure that you can actually internalize and understand this information. So take a moment and jot down, what does atomic radius mean to you in your own words? In the periodic table, we'll notice certain trends that emerge as we move down a column and across a row. The first thing that happens as you move down a group in the periodic table is that the atomic radius increases. And this makes sense because as you move down this column here, you're getting a larger and larger and larger atom. You have more protons, you have more neutrons, you have more electrons occupying larger and larger orbital energy shells. So it makes sense that atomic radius will increase as you move down the periodic table. What's interesting and might be a little bit counterintuitive is the idea that atomic radius actually decreases as you move across a row, if you can imagine. So let's think about that for a moment. As I move across the row from left to right, I have more protons, more electrons, and you can kind of think of this like magnets. If you have two magnets, you know, they're going to have a level of attraction, but if you have multiple magnets, they're going to have a stronger attraction. So think of the protons and electrons like oppositely charged magnets. They're going to be the protons of the nuclei on this far end are going to be holding their electrons really, really tightly. And there's something that happens here too with the amount of energy, and we're going to talk about that in a little bit as well. So atomic radius increases as you move down a group, decreases as you move from left to right across a period. Now take out your periodic table because I want us to write that down somewhere on our periodic table. So we're going to make a note that as we move down this group here, down this column, atomic radius increases. As we move across the row, I'll draw one down here. And you could do the same. Our atomic radius decreases. As those larger amount of protons and electrons hold one another more tightly. The reason the atomic radius increases down a group is due to the fact that atoms are simply larger as you move down a group. And as a review, as you move across the period, there is a stronger attraction of electrons to protons because there are simply more of both of those oppositely charged particles. In other words, those atoms are held more tightly together as you move across the period. Now we're going to talk a little bit about valence electrons. Valence electrons are electrons that are in the outermost energy levels of an atom. These are the electrons that are farthest away from the nucleus of the atom, and they are the ones that are most likely to participate in chemical bonding. They're the ones who are most likely to interact with other elements to form bonds and form molecules. The most likely to be gained or lost in a chemical reaction. So the gaining and losing of electrons is what will form bonds with other elements. Each group, that is to say, each column on the periodic table will have the same number of valence electrons. And today we're going to take a look at how to calculate that number of valence electrons. So to determine the number of valence electrons, all you do is you simply count boxes from left to right. And the number of boxes that you count is the number of valence electrons the atom has. So let's take a look. Carbon, for example, has 4 valence electrons. Nitrogen has 5 and neon has 8. And the way that I got that is simply by taking a count. Carbon, we'll start here, 1 valence electron, 2, 3, 4. So carbon has 4 valence electrons. Nitrogen has 5, oxygen would have 6, and so on and so forth. So you're simply counting across 1, 2, 3, 4, and you'll start to notice some trends happen. That everything in this row will have 1 valence electron. Everything in this row will have 2 valence electrons. Everything in this row will have 3 valence electrons. So take a moment and you're on your periodic table and label each of these outer edge groups from group 1, group 2, group 13, 14, 15, all the way to the end here with the correct number of valence electrons. 4 valence electrons, 5 valence electrons. And then we'll go back and we'll see if we can predict the correct number of valence electrons based on its position on the periodic table. Now it's our turn to practice. How many valence electrons would you say helium has? What about silicon? What about calcium? Look on your periodic table and fill in the blank with the number of valence electrons each of these has. I'll do the same, and then you can pause and check your answers. Let's see how you did. Were you able to tell that helium only has 2 valence electrons? Silicon, on the other hand, is going to have a slightly different number. They're going to have 4. They're in the same row as carbon, so they end up having the same number of valence electrons. Calcium has 2. It's in that second row, so it's going to have 2 valence electrons. The next topic we're going to talk about is relative reactivity. How do elements in each group compare to each other in terms of their ability to react with other substances? Valence electrons are those that are in the highest energy orbital, and it makes them high in energy. The atom prefers to have, everything prefers to have low energy. Low energy corresponds to stability. So an atom would be most stable in its lowest energy state, and thus it prefers to have full energy level of 8 valence electrons. We call this the octet rule. So an atom is the most stable when it can somehow manage to beg, borrow, and steal 8 valence electrons. It either does this by virtue of having its own 8 electrons, such as in the example of the noble gases, or it can form a bond with an element that has a number of valence electrons that added together would equal 8. So what does this mean when we look at our periodic table? Well, if you think about the elements that are in this first group, the ones that have 1 valence electron, they tend to want to get rid of that 1 valence electron, because in doing so, they'll settle back down to their next lower energy state with a full 8. They tend to be highly reactive with the elements in this group that have 7 valence electrons. So elements here with 7 valence electrons love to form bonds with these 1 valence electrons, because when they do so, they're able to share a stable 8, a stable octet of electrons. Funny enough, the elements in this column, our noble gases, they already have 8 electrons. They tend to not want to form bonds with anything else. That's why we call them the noble gases. They're functionally inert. That is to say, they don't like to make bonds with other elements because you know what? They're good with their 8 octet already. So to review, the reason that the halogens, our group 17 with 7 valence electrons, are so reactive is that they are only 1 electron away from fulfilling their full octet. And so they will react very quickly, especially with something that has 1 electron in order to gain that extra electron and make a full set of 8. Likewise, those alkalis, the group 1, that have 1 extra electron, they will quickly react to remove themselves of that extra electron and settle back down to a stable 8 configuration. So that's it for today. I hope that you're able to use the periodic table to compare one element to another in terms of its relative reactivity and its atomic radius based on its position on the periodic table. You should also be able to count up the number of valence electrons in a given element based on its position on the periodic table. I hope you're doing well and have a great day.